Hello. First of all, I would like to thank you for attending this presentation. My name is Ibrahim Farhat, and today I'm going to present my PhD entitled Efficient Hardware Designs of the New Versatile Video Coding Tools for ASIC Platforms. This work was conducted in a collaboration between the VITEC company and the UTL laboratory, and it was finalized in 31st of May 2022. The outline of this presentation is as follows. First, I will start by an introduction. Secondly, I will present the proposed hardware implementation for the VVC transform design for the decoder context. Thirdly, I will present the proposed hardware implementation for the adaptive loop filter for the decoder context also. Then I will present the adaptive loop filter hardware design, but this time for the encoder context, and I will finish by a conclusion. So let's start by the first part. And this part will present the evolution of video consumption. We will answer the question of what is video coding. We'll present a specific video coding standard entitled the Versatile Video Coding, and we'll finish by summarizing the PhD contributions. So in fact, over the time, video consumption has increased significantly. For video display, we went from a simple television set to a variety of displays, TV, computers, tablets, and smartphones. Also, video usage has increased, coupling social networks like Facebook, specific video platforms like YouTube and Netflix, streaming and gaming platforms like Zoom and Twitch. In addition, new video formats are emerging. For spatial resolution, we have 4K, 8K, high dynamic range videos, and also high frame rate and 360-degree videos are emerging. Now, according to a study published by Cisco, video consumption is constantly increasing. It is estimated to cover 80% of all internet traffic by year 2023. Now, all of this breeds the need for an efficient method to reduce the size of raw videos, which is video coding. So what is video coding? Video coding is composed of two parts, an encoder and a decoder. At the encoder side, it receives the source video and generates a sequence of bits called bit stream. At the decoder side, it deciphers the bit stream to generate what is called the reconstructed video. In fact, the coding process is actually standardized. Since 1998, MPEG and VSEG groups have been trying to cope with the evolution of video consumption. In 2003, they were able to standardize the most famous video coding standard, Advanced Video Coding, to support HD videos. In 2013, the famous HVC was standardized to support 4K videos, and recently, in July 2020, the new Versatile Video Coding standard was released to support 8K, 360, and HDR videos. Now, every time each video coding standard tries to enhance 50% the quality for the same bitrate. In fact, VVC was successful to reach this objective. It introduces 30 to 50% better quality, however, with the expense of larger complexity. VVC is estimated to be 8 times more complex compared to HVC for the encoder context, and 2 times more complex compared to HVC for the decoder context. The purpose of this PhD is to propose some hardware implementations for the VVC standard, for the encoder and decoder context. Now let's take a deeper look into the VVC block diagram. In fact, VVC is composed of multiple tools based on the famous hybrid video coding technique. As we can see from the figure, it is composed of prediction phase, which has 2 types, intra-prediction and inter-prediction. For intra-prediction, it tries to predict samples from neighboring samples of the same frame. Inter-prediction, on the other hand, tries to predict samples using previously received frames. This is by exploiting algorithms such as motion estimation and motion compensation. Now, the predicted frame is subtracted from the original frame and to generate what is called the residuals or prediction error. These residuals are then processed by the transform and quantization phases. The transform will actually convert the value of the residuals from spatial domain to frequency domain. Then the quantization will eliminate frequencies that are not visible by the human visual system. In fact, because of the use of the quantization, the encoding process is actually lossy. Therefore, the encoder embeds a decoding loop inside it, for the purpose to mimic the behavior of the decoder. Therefore, it applies the inverse transform and inverse quantization. In addition, the decoding loop uses an in-loop filter process that enhances the quality of the decoded frame. This latter is stored into a decoder picture buffer. Then the loop goes again, and the prediction starts over. And finally, in fact, the end stage of the encoding process is entropy coding, which receives the quantized coefficient and generates the sequence of bits or the bit stream. In fact, in this PhD, we focus on three main modules: the transform, inverse transform, and the in-loop filter phase. In the transform, we will study the MTS, LF, and ST, and in the in-loop filter phase, we study the ALF. These tools we will come to explain later. Here, an important note here is that before the encoding process starts, every frame is actually divided into a sequence of blocks called coding tree units that have sizes from 16 by 16 to 128 by 128. These blocks are also divided into a sequence of CUs that could have sizes from 4 by 4 up to 128 by 128. These CUs, like the CTUs, include asymmetric blocks. In fact, at the level of transform, prediction, and quantization, CUs are the one being processed, while at the level of in-loop filter, the CTUs are the one being processed. In fact, the CTUs are the element blocks at the level of in-loop filters. Now, let's move on to the PhD context. Since the objective of this PhD is to propose some hardware implementations for the VVC standard, let's take a look at what kind of application actually requires dedicated hardware solutions. For broadcast, we have stream live broadcast quality content to any device. Here we have an increasing demand for better user experience. For stadiums, arena, and entertainment events, where we have unique requirements for effective and reliable solutions. For military, where we have mission-critical application with strict requirement for real-time and high quality. Now, all of these applications could only be achieved by using dedicated hardware solutions. Also, IC providers like ST, LG, Intel, and many other companies uses video IPs for their target applications. In fact, in this table, we compare the performance of the VITEC hardware encoder compared to the HHE software encoder. The aim of this table is to show what the number of cores required when aiming to encode 4K P60 videos in real time. As we can see from the table, the hardware VTech encoder is actually 80 times more efficient in core usage. In order for the HHE software encoder to be able to process 4K P60 videos, it requires at least 295 cores for its fast mode. This is actually a theoretical study. However, the VTech hardware encoder in practical requires only 4 cores to process 4K P60 in real time. Now let's take a look into the feature of the hardware encoder, encoder and decoder. As we can see here, the hardware codec should be able to process in real time 4K videos with 60 frames per second. It should be able to support all bit depth 8, 10, and 12, all chroma subsampling up to 422 chroma subsampling. For the decoder context, all recent MPEG video coding standards should be supported: VVC, HEVC, and AVC, while for the encoder context, only VVC video coding standard is supported. The objective is always to minimize as possible the silicon area and to minimize also as possible the power consumption. Now, in the context of the decoder, in this PhD, we propose the hardware implementation for the inverse multiple transform selection and the hardware implementation for the inverse LFNST, and also another one for the adaptive loop filter. For the encoder context, also we participated by proposing some hardware designs for the transform for the encoder context, which is different. And also we proposed the hardware implementation for the adaptive loop filter for the encoder context, which has a decision and a filtering phase. Now let's start by the first contribution of this PhD, which is the proposed hardware implementation of the VVC transform for the decoder context. This part will present the VVC transform concept, the requirements in the context of the decoder, the proposed transform hardware architecture, and we'll finish by presenting the results and performing some analysis. So the VVC transform concept, as we said, the VVC transform is actually composed of two transform types, the MTS and LFNST. It is applied on transform blocks that could have sizes from 4x4 to 64x64, including asymmetric blocks. The MTS stands for multiple transform selection. It is a separable transform. It has three transform types: DCT2, discrete cosine transform of type 2, DCT8, and DST7, discrete sine transform of type 7. In fact, for DCT8 and DST7, these transform types are limited to blocks of size 32 by 32, while the DCT2 goes all the way to block sizes of 64 by 64. At the encoding process, the encoder will test multiple combinations of horizontal and vertical directions. In fact, if the DCT2 is used for horizontal direction, it is used for vertical direction, as you can see in the figure. However, combinations between DCT8 and DST7 are allowed for horizontal and vertical direction, as we can see in the figure. The LFNST, on the other hand, stands for low frequency non-separable transform. It is a non-separable transform unlike the MTS. It is only applied when the DCT2 is selected for the MTS. It is applied on low frequency components and has kernel sizes that could be of size 16 by 16 and 16 by 48. As you can see in the figure, it is applied after the DCT2 on the encoder phase and tests a maximum of 2 kernels for every intra mode. Let's dive in more into the multiple transform selection. As we said, it has three transform types: DCT2, DCT8, and DST7. As you can see from the equation of DCT2, the transform size n is actually linear. This fact allows us to deduce smaller transform sizes from larger ones. As you can see in the figure, here we show the example of 16 by 16 DCT2 matrix. In fact, we are able to deduce the 8 by 8 DCT2 matrix directly by selecting the even positioned columns. The same for 4 by 4 DCT2 matrix. We can select directly even positioned column of the 8 by 8 matrix and retrieve directly the 4 by 4 DCT2 matrix. This fact allows actually the VVC standard to define only 64 by 64 matrix, and all other matrices are directly deduced from this one. Also, the DCT2 has another feature called the butterfly, which allows for multiplication reduction. The DCT8 and DST7, on the other hand, does not have any specific features like the decomposition of the DCT2 and the butterfly, but it has a specific feature, which is a specific relationship between the DCT8 and DST7 that allows the deduction of one from the other by using simple permutation and sign changes matrices. The VVC in this case defines all matrices from 4 by 4 to 32 by 32 for the two transform types. The low frequency non-separable transform, on the other hand, is applied after the MTS and before the quantization at the encoding process, and before the inverse MTS and after the inverse quantization at the decoder process. It uses two indices, LFNC set index and LFNC index, to determine the used kernel. It is applied on low frequency coefficient. It is applied up to 48 input samples at the encoding process and 16 maximum input samples at the decoding process. The VVC actually defines 16 total kernels to be used for the LFNST. Now let's move on to the transform requirement in the decoding process. In fact, as we said, the hardware decoder is expected to support 4K P30 videos for 4:2 chroma subsampling at a frequency of 450 MHz. Now, in order to define the performance or the speed of the transform, we compute the pixel level rate. In order to compute this, we divide the resolution, the area defined by the resolution in 1 second, by the total frequency, and as we can see, the result is 2 pixels per cycle. In fact, this result 2 pixels per cycle is actually for 2D transform. However, for one directional transform, it requires at least 4 pixels per cycle in order to process 4K P30 videos in real time. In this case, the requirements for the transform is to propose hardware implementation that includes all MTS types, DCT2, DCT8, and DCT7, the LFNST also, supporting all CU sizes up to 64 by 64 with the sole objective to minimize as possible the silicon area. Now let's take a look into the proposed hardware implementation. As we can see from the figure, the proposed design has 2 pipeline stages. The first stage computes the LFNST, and the second stage computes the MTS. Now, when the first direction of the MTS is applied, the LFNST actually transforms the data and delivers the output to the first direction of the MTS. However, when the second direction is selected, the LFNST is bypassed and the input are directly connected to the second direction of the inverse MTS. Now both module, the LFNST and the MTS, uses the same architecture. They both embed 3 submodules: the ROM, read-only memory, a coefficient preparation module, and a core multiplication module. The read-only memory will store the coefs and the data defined by the VVC for the LFNST and MTS. The coefficient preparation module will select a certain number of coefficients depending on the input status, and the core multiplication module will apply the transformation process using 64 multipliers in parallel in order to respect the 4 pixel per cycle throughput. Now let's move on to the results. In fact, at first we designed the inverse MTS, hardware architecture using constant multiplier based architecture, and as we can see from the table, we then implemented this inverse multiple transform selection using regular multiplier based architecture. We noticed it then from an area perspective, the constant multiplier based architecture is 2.5 times more area than the regular multiplier based architecture. This proves that a regular multiplier based architecture is more efficient for the transform of VVC this time. We then synthesized the inverse MTS and the inverse LFNST for 2 different throughputs, 2 pixels per cycle and 4 pixels per cycle. As we can see in the tables, doubling the total number of pixels per cycle ended up in doubling the total number of multipliers. From an area perspective, the MTS has 35% augmentation in area compared to the 2 pixels per cycle. The LFNST had 31% augmentation in area. And now if we compare them against each other, we notice that the inverse MTS has 22% more area compared to the LFNST. Now, in order to further evaluate the VVC transform, here we show a comparison between the VVC transform and the HVC transform. As we can see from the table, the VVC transform actually has larger transform types and supports non-separable transforms, while the HVC transform has limited transform types and does not support the non-separable transform. In terms of block sizes, the VVC transform supports up to 64 by 64 block sizes, including rectangular blocks, while HVC transform is limited to 32 by 32 block sizes with and does not support asymmetric blocks. In this table, actually, we used 2 different architectures. For the VVC transform, we used a regular multiplier based architecture, while for HVC transform, we used constant multiplier based architecture. This is because these 2 architectures are proven to be efficient for their transforms. In terms of surface, we notice that the VVC transform is actually 5 times has 5 times augmentation in area when including separable and non-separable transform, that is MTS and LFNST, and when eliminating the LFNST, which is the non-separable transform, and compare only separable transform against each others, we notice that the VVC transform is actually 2 times larger than the HVC transform. Now, all of this is considered to be reasonable since the VVC transform actually introduces new transform types and supports larger transform blocks. Now moving to the second part of this presentation, which is the proposed hardware implementation of the ALF design for the decoder context. In this part, we'll present the ALF concept, the ALF requirement for the decoder context, the challenges in the context of the decoder, and some scanning scenarios that resolve these challenges. And after that, we'll present the proposed hardware implementation for the ALF, and we will finish by presenting the results and performing some analysis. So let's start by the concept. The ALF, as we know, is a part of the in-loop filter process. In this process, we have three main filters. The deblocking filter, DBF, which tries to smoothen the edges of CTUs. The sample adaptive offset, which tries to remove artifacts such as ringing. And the adaptive loop filter, which removes artifacts such as blurring. In fact, to do so, it uses three filters, one for luma and two for chroma, the 7x7 diamond shape filter for luma, and the 5x5 diamond shape filter and the cross-component adaptive loop filter for chroma. Let's start by the luma filter. In fact, for the luma, we have two main parts. The first part computes the gradients for multiple directions. In this part, we compute the gradient in order to find the set of coefficients used for the 7x7 diamond shape filter. In fact, as we can see here, the ALF computes gradients for multiple directions, vertical, horizontal, diagonal up, and diagonal down. It computes these gradients by computing the sum of Laplacians, which is the measurement of variation in a direction, intensity variation in one direction, as you can see in the figure. And then it sums up these gradient value to determine the sum of gradient for the specific direction. Now, after computing all gradients for all direction, every 4x4 block is actually classified into a value between 1 and 25. This value actually enables us to determine the filter coefficient. Now, as you can see from the figure, the 7x7 diamond shape filter is actually symmetrical. Therefore, only 12 coefficients are required. As we can see from the figure, the 7x7 is actually symmetrical. In addition, these coefficients are actually of two types: a fixed filter coefficient, which are 25 filters defined by the VVC standard, or custom filter coefficients, which are filters created by the encoder and signaled directly to the decoder via the adaptation parameter set. The chroma filter, on the other hand, uses two filters, the 5x5 diamond shape filter and the cross-component adaptive loop filter, as we can see in the figure. Unlike luma, these filters does not require any gradient computation or classification process. The 5x5 DSF uses only custom filters in APS, since it uses also only 6 coefficients, since the filter is symmetrical, as you can see in the figure. Cross-component ALF uses collocated luma samples in order to filter chroma ones. Here we show the example of 420 chroma subsampling. As we can see, the filter is actually positioned onto a collocated luma sample to apply the filtering process. The coefficient for this CLF are also signaled, are also custom by the encoder and signaled in the APS. Now, the requirements are similar to the transform ones. The ALF is designed as part of a decoder, a real-time decoder that supports 4K video for 30 frames per second for 422 chroma subsampling, with a target frequency of 450 MHz. As we can see, when we divide the area defined by the resolution and the frequency in 1 second, we determine the pixel rate, which is 2 pixels per cycle. This is the restriction in order to be able to process 4K videos in real time. Now, the requirement in this context is to propose a hardware implementation that supports all ALF filters, the 7x7, 5x5, and CCALF, supporting also all CTU sizes, with the sole objective is to minimize as possible the silicon area and the memory cost. The challenges for the ALF. For the ALF, we actually have many challenges. Here we list the two main challenges. In fact, as we can see from the figure, every 4x4 luma block or 4x2 chroma block actually requires the 8 surrounding neighbors from top left to bottom right in order to apply its filter. This means that we need to store, when we scan blocks in raster scan order, we need actually to store 2 lines and 2 columns of 4x4 Luma blocks and 4x2 chroma blocks. At least these 2 lines are required in order to filter an entire Luma or chroma CTB. For the cross-component adaptive flow filter, the challenge is different. As we know, here we can see in the figure, every chroma block actually requires 2 filters, the CCALF and the 5x5 diamond shape filter. In order to finish filtering one CTB block, the resulted filtered CTB is actually the sum of the 2 filters, the cross-component ALF and the 5x5 diamond shape filter, as we can see in the slide. However, here when we process the chroma CTB, co-located Luma samples are actually required for the cross-component ALF. Therefore, at the moment of processing the chroma CTB, the question here, do we need to store the entire Luma CTB in memory in order to finish filtering one chroma CTB? In this case, the memory expected are very large. So how to optimize this and reduce the memory for this CLF requirement? In order to see how to optimize this, we go actually through multiple scenarios. The first scenario is that we scan Luma CTBs first. Here we show the example of 420 chroma subsampling. We scan one Luma CTB followed by one chroma CR CTB followed by one chroma CB CTB. In this scenario, we are actually required to store an entire Luma CTB in order to filter the chroma CTBs. In addition to that, for the 5x5 diamond shape filter, we need to store 2 lines and 2 columns of 4x2 blocks. The second scenario is that we scan the chroma block first. At first, we scan the chroma CR, followed by the chroma CB, followed by the Luma CTB. In this case, we are required to store actually the filtered chroma versions using the 5x5 diamond shape filter, alongside with 2 lines and 2 columns of 4x2 blocks, waiting for the Luma CTB to be present in order to finish filtering the chroma CTBs. In addition, Luma CTBs, as we can see in the figure, require also at least 2 lines and 2 columns of 4x4 blocks. Now, these 2 scenarios made us conclude that the best solution for an optimal memory is that to find an alternation between Luma and chroma blocks that enables the parallel execution of the CLF and the 5x5 diamond shape filter. Therefore, the scenario 3 was defined. In this scenario, which is the proposed scenario, we actually scan one chroma CTB, one chroma CR CTB, and one chroma CR block of size 4x2, followed by one chroma CB block of size 4x2, followed by 2 Luma blocks of size 4x4. And we continue this scanning for the entire line of CTB. Then we continue the scanning order for the entire CTB, as you can see in the figure. This alternation actually enables us to process the cross-component adaptive loop filter and the 5x5 diamond shape filter of the chroma in parallel with the minimum possible use of memory. In this table, actually, we compare the 3 scenarios. As you can see, for the first scenario, it requires at least 178 and 78 kilobits of RAM in order to apply the 3 filters. For scenario 2, it requires 116 kilobits of RAM, and the scenario 3, which is the proposed scenario, actually consumes 35 kilobits of RAM, which is 20% of the first scenario. And here we introduce 80% gain compared to the first scenario, which is the solution that got adapted for our hardware implementation. Now, the hardware implementation is composed of 2 pipeline stages. A first stage that deals with the memory access and the random access memory and the memory handler. A third stage, a second stage, which handles the gradient computation and the filtering operation. As we can see in the first pipeline stage, the memory access receives input block, and depending on the position of the block within the CDP, the memory handler will decide whether to store this block into the RAM or to deliver it to the second pipeline stage. When Luma blocks are being processed, as we can see in the figure, every block is delivered to the second pipeline stage, which with its 8 surrounding neighbors from top left to bottom right. When Luma blocks are being processed, the gradient module is executed to compute the sum of gradients, and this module is actually composed of 3 submodules. The gradient sum, which computes the sum of gradients for all direction. It determines the classification value, which in turn selects one single coefficient from the fixed coefficient row, and also a third module, which applies a certain transposition to every filter depending on the gradient sum results. The gradient module will finally generate coefficients, the filter coefs, which will then be processed by the filtering module. This module is a unified for all ALF filters, and it has 3 pipeline stages, as you can see in the figure, and finally it uses 26 multipliers in parallel in order to process 2 pixels at every clock cycle. And this module is actually unified for the 7x7 dimension, 7x7, 5x5, and cross-component ALF. In this table, we show the results for the ALF hardware implementation. As we can see, the total area consumed by the ALF is actually around 67,000 micrometers square of area, with a power consumption of 9.5 milliwatts. As we can see, 45% of the total area is consumed by the memory access module, 22% by the gradient module, and 27% by the filtering module. Compared to the state of the art, we are the only solution that proposes a complete hardware implementation for the ALF, targeting ASIC platform. It supports, this solution aims to support, as we said, 4K videos decoding in real time. As we can see, we are the only solution to propose a study for the gradient sum and the cross-component ALF alongside the memory. Now let's move on to the last part of this presentation, which is the proposed hardware implementation for the adaptive loop filter, but this time for the encoder context. In this part, we'll present firstly the encoder context. Then we'll present the proposed hardware implementation for the Luma filter design, followed by the decision design, and we'll finish by presenting the results and performing some analysis. Similar to the decoder, the encoder is actually expected to process 4K P30 videos for 422 chroma subsampling in real time, with a frequency also 450 MHz. Unlike the decoder, the encoder has 2 phases for the ALF, a decision phase and a filtering phase, which belong to the decoding loop. In fact, after a deep study performed by the algorithmic team, the ALF actually catches most of its coding efficiency when supporting CTUs of size 64 for Luma samples only. Also, if we apply the same, if we compute the decision over 4 filters, the ALF also remains efficient for the encoding process. In addition, the hardware team and the hardware decoder, the hardware encoder actually defines a certain clock budget for each CTU64. As we can see, the clock budget is actually set to 9,000 cycles. For both the decision and the Luma filter, the entire process should be finished in 9,000 cycles, as you can see in the figure. However, now to compute the pixel rate level at the decision and Luma filter, as we can see, we divide the area defined by the Luma filter and the decision. We find that for both phases, we could process 1 pixel every clock cycle, and we are able to reach this encoding in real time. However, for security reason, because it is at the limit when processing 1 pixel per cycle, we actually increased the pixel rate of the second phase to 2 pixels per cycle. Therefore, in this context, the decision should process 1 pixel every clock cycles, while the Luma filter will process 2 pixels every cycle. Now let's take a look into the top level design of the ALF filtering phase, which is the second phase. Similar to the decoder, it is composed of a random access memory, a memory handler, a gradient computation module, and the filtering process, which applies the 7x7 diamond shape filter. Here, unlike the decoder, in this context, the chroma filters are eliminated, therefore only the 7x7 diamond shape filter are applied. The gradient is similar to the decoder also. It uses 3 submodules: the one that computes the gradient sum, the ROM, read-only memory, which stores the fixed filter coefficient, and the kernel transposition module, which applies certain transposition to the filters depending on the gradient sum results. The gradient sum will generate finally the coefficient required for the 7x7 diamond shape filter, and this latter is executed over 3 pipeline stages, and it uses 24 multipliers in parallel in order to process 2 pixels every clock cycle. The decision phase, on the other hand, has multiple submodules. Unlike the first phase, it has similar to the first one. It uses a random access memory and a memory handler. It also applies the gradient computation, the gradient sum, since it is applied for Luma samples. And then it uses 4 filters. It applies 4 filters along the case where the ALF is not applied. And then using a sum of square difference module, it computes the sum of square differences between the filtered blocks and the non-filtered blocks and the source block. Then as a final result, the decision phase will select the filter that minimizes the SSD, or the sum of square difference, as we can see in the figure. Now let's move on to the results. For the Luma filter phase, which is the second phase, we synthesized this module for 28 nanometer ASICs with 0.8 volt input voltage. We note that the total area of the design is around 42,000 micrometers square, with a power consumption of 6.0 milliwatts. As we can see, most of the area is consumed by the memory handler and the RAM, with 38% of the total area. The least consuming module is the gradient module, with 28.9% of the total area. The first phase, the ALF decision phase, is synthesized for the same environment as the filtering phase. The result showed that the total area consumed by the ALF decision is around 16,000 micrometers square of area, with a power consumption of 7.8 milliwatts. As we can see, most of the area is consumed by the 7x7 diamond shape filter, which has 4 units this time, in order to compute the 4 filters in parallel, to test 4 filters in parallel. This one consumes 52% of the total area, with the least consuming module is the SSD module, with around 5.5% of the total area. Now, in order to further evaluate the adaptive loop filter, here we compare the results we got for the ALF for the encoder context and for the decoder context. First of all, as we can see from the table, the ALF decoder actually supports all filters, 7x7, 5x5, and CCLF, while the encoder one supports only the Luma filter. In terms of CPU sizes, we notice that the ALF decoder supports up to 128 by 128 CTUs, while the encoder one supports only CTUs of size 64 by 64. In terms of regular multipliers or parallel multipliers, here for the decoder we used 26 multipliers in order to process 2 pixels per cycle, to the throughput of 2 pixels per cycle, while for the ALF encoder we used a total of 72 multipliers for both the Luma filter and the decision phase, in order to process 2 pixels per cycle for the Luma filter and 1 pixel per cycle for the decision phase. Now, in terms of random access memory, we notice that the ALF encoder phase has 48% more random access memory, more memory consumed. From an area perspective, 33% more silicon area for the encoder also, and from a power perspective, 32% more power consumption compared to the decoder one. Here we can conclude that this result is logical, since the ALF encoder has two phases compared to one phase for the decoder one. Now moving to the conclusion. In this presentation, we showed how video consumption increased, the augmentation, and we presented some new video formats. We also presented the block diagram of the versatile video coding. Then we presented our proposed hardware implementation for the inverse MTS and inverse LFNST. In this part, we showed that using regular multiplier-based architecture is more efficient for the VVC transform compared to the previous HVC transform. This solution actually got integrated into the hardware decoder with 3% of the total VVC decoder. Then we presented our proposed hardware implementation for the adaptive loop filter. Here we showed, we presented our novel scanning order that optimizes the memory consumption. This solution also got integrated into the hardware decoder with a total of 0.8% of the chip surface. Finally, we presented our proposed hardware implementation for the adaptive loop filter for the encoder context. In this phase, in this part, we showed that the ALF encoder has two phases, a Luma filtering phase and a decision phase. This solution also got integrated into the VVC encoder with 0.67% of the total area. As a conclusion, as a part of perspective, in fact, a shared design between the inverse LFNST and the inverse MTS could be studied and compared to our proposed design for the VVC transform when separating the inverse MTS and the inverse LFNST. Also, machine learning could be used for the encoder transform by designing a training net using the results of encoded frame database. This will possibly reduce the rate distortion exhaustive computation. The ALF decision also could make use of the machine learning algorithms by taking advantage of ALF decision encoded database. This will eliminate the computation of local RDOs for ALF. In addition, system-on-chip designs to accelerate software solutions could be also exploited. We noticed for the OpenVVC of the IETR laboratory, the ALF actually consumes 30% of the total runtime complexity. Therefore, this one could be put onto an FPGA and adding some communication between a hard processor system and an FPGA, we could reduce the runtime complexity for the ALF. Here we present our publication during the PhD. I would like to thank you for your attention.